Alright, this is a pre-algebra chapter 1, lesson 7. We're going to talk about computing with scientific notation, doing calculations with scientific notation. Now, our objective is, as the student, I can compute with numbers in scientific notation because I will apply my knowledge of exponent operations, such as the things that we learned earlier in this chapter. And in other words, I want you to pretend that the 10 in the scientific notation, pretend it's like a variable. So for example, as a quick example, if we had 5.4 times 10 to the 4th power times 3.2 times 10 to the 3rd power, what you could do is you could rewrite that and pretend that what you can do, guys, is that original number, that 5.4, you can pretend that's the coefficient, and you can make that the coefficient, and instead of times 10, just make it touching the x, because remember, times 10 and times x, we're kind of saying they're like the same thing. And then you notice the exponent is the same. Then we did the same thing for the 3.2. So now that you have it in this format, you now are prepared to be able to do it like we did in an earlier video with how to multiply with exponents. And in other words, you'll actually multiply those coefficients. So 5.4 times 3.2, and by the way, that gives you 17.28. You'll multiply those together, and then you would take your variable, your x, and you would add those exponents. We learned that's the product property of powers. When you multiply, you add exponents. So you'd have x to the 7th power. But since, remember, technically this was a scientific notation question, feel free to go ahead and put back scientific notation in there now. So you can either write x to the 7th power now and then go back to that, or once you get good at it, you may skip this step of turning into an x. You might just want to go straight to writing the answer, so times 10 to the 7th power. So that would be the answer to this question. 17.28 times 10 to the 7th power. And this would be an example of a calculation that maybe a scientist would use when describing some really far distances with some really large numbers. This number is much easier to work with rather than saying what it really is, which, by the way, would be 172,800,000. That's a bit of a mouthful, and it's harder to talk about, calculate with that. So we put it in scientific notation so that we can do so. We're going to do some more examples in just a minute. So here we have a new example. Let's say the item on the left, we see that it has a negative exponent in scientific notation. That means it's a very small number. So for example, maybe that's like the weight of something. So think of something really light, like maybe the weight of a strand of hair. Although, to be honest, that would be even lighter than that. But let's pretend it was the weight of something really light, like a grain of sand or a grain of salt or a grain of rice. And then the number on the right could be how many of that item do we have. So for example, let's say we were doing rice. Let's pretend the left side was the weight of the grain of rice. The right side, you see it's a positive exponent, which means it's a really large number. So we can pretend that that's going to be how many grains of rice do we have. And so the idea is, in this question, if we multiply them together, we might be asking, what is the total weight that we have altogether of the rice? So this would be an example where we're going to use scientific notation and use our exponent property rules instead of doing it with the long drawn-out numbers. Because sometimes those numbers are so big or so small, and as far as also having lots of digits, that they won't actually fit even on an 8-digit calculator. That can happen. So let's see. For the very first one, let's pretend. For the visual, I'm going to remind you how I did it in the first screen. You could pretend that times 10, pretend instead of that, pretend it was 3.4 was the coefficient and the times 10 was the variable. And I say that because notice, both of these have a times 10 in them, which means we can multiply these and add the exponents, or we can divide these, if it was a division problem, and subtract the exponents. That's what I mean. So we could pretend that this is 3.4 x to the negative 3 power times 1.2 x to the 4th power. So that's how we could pretend this question looks. Now, when we did these, we learned before that when you multiply these, if you have coefficients, go ahead and multiply the coefficients. So if we were to multiply those, we would get 4.08. So that means our answer would be 4.08 times, I'm getting this ready for scientific notation, but anyways, over here we'd have 4.08, and then x, we would add the coefficients. So let's see, negative 3 plus 4. When you multiply, negative 3 plus 4 is positive 1. So that's 4.08x to the positive 1 power. Or over here, that's 4.08 times 10 to the positive 1 power, since we said the x is like saying the times 10 part. Anyways, so that's our answer. Now let's say because it's only 10 to the first power, we could say this in a realistic way without it being a mouthful. For example, 4.08 times 10, it's 10 to the first power, it's just like saying times 10. Well, that's 40.8. So 40.8 is maybe the realistic number. We could say, like if we were talking the weight of something, maybe that's how many grams or grains we have of total weight. This could be, sometimes if you get an answer in scientific notation that could be translated to something reasonable that we can understand, that doesn't sound like a number we would normally use, you're good to go. And you can go ahead and actually do it. Let's say we have this question at the bottom. Let's say we were told that the largest planet in our solar system is Jupiter, and it has a diameter of about 143,000 kilometers. And I went ahead and translated that scientific notation if they didn't do so for you already. Then we go on and would say the smallest planet in our solar system is Mercury, and Mercury has a diameter of about 5 times 10 to the third power kilometers. Now here's the important part. About how many times greater is the diameter of Jupiter than the diameter of Mercury? I said how many times greater, meaning I think you can tell just from looking at the scientific notation, clearly Jupiter is the larger one because it has the bigger exponent. And so Mercury is going to be the smaller one. But when it says how many times greater, we're asking how many times does the size of Mercury go into the size of Jupiter when it says how many times greater? So this is a division question. That's what this is. So in other words, we're going to go ahead and divide that. It's almost as if saying, if we divided the size of Jupiter by the size of Mercury, the answer is going to be how many times Mercury goes into it, which is going to tell us how many times bigger it is. So let's set this up as a division problem. So here we have it written up as a division problem using a fraction bar, and now we're ready to do this. And like I said earlier, if you pretend that this was almost like the quotient property of exponents, we could do this. Pretend that times 10, pretend it was just a variable. And by generic, I tend to just use x because it's a generic variable. But set this up, maybe think of it that way if that helps you. So I'm going to go rewrite it that way just to help you see it. And what we learned in those videos, I wrote on the right, it is if it was almost like a monomial divided by a monomial type of problem. If we have coefficients, go ahead and straight up divide them. So 1.43 divided by 5. And that's going to give us 0.286 is what that's going to give us. So I'm going to go ahead and write that in. So 0.286, and then we now are going to subtract the exponents. So if we were doing the example on the right side, we would do 5 minus 3, which would give us 2, so we have x to the second power, 0.286. And now same thing on the right side. So, but instead it's going to be times 10 to the second power, since 5 minus 3 is 2. So this isn't proper scientific notation. So what we would do is put it into scientific notation by maybe imagining we want to see this moved over one more time so it was in scientific notation. But if we do that, this 2 is going to go from a 2 into a 3, so that now that would, oh, I'm sorry, I did that in the wrong direction. It's going to be to a 1. Because we made it bigger already. If we made it to a 3, it's going to get even bigger, so that 2 is going to become a 1. There we go. And that's because it doesn't have to move as many decimal places to get back. So we're going to have 2.86 times 10 to the first power. That's how many times bigger it is. Maybe that doesn't quite make sense, and like we did in that last example, 10 to the first power is not a big deal, so let's go ahead and actually do that. And that's going to give us 28.6. So that's going to tell us Jupiter is 28.6 times larger than Mercury. However, I did say in the question, I did technically say about how many times larger is it. So let's go ahead and just round that to the nearest whole number. So for that reason, we would say it's about 20 times larger. That's how much larger Jupiter is than Mercury. Sorry, I got squished with the larger. And this was another example of doing calculations with scientific notation. Make sure you copy these down before we move on. I'm gonna let you do a few more. I'm gonna let you now do a few examples on your own, and I'll let you check yourself, and then we're gonna be all done. But of course, I forgot. We gotta make sure we do addition and subtraction first. I'll do one example of each, and then I'll let you do one of each on your own. So we gotta do addition and subtraction real fast, and then we'll be ready. Okay, so now we're going to do some examples of adding and subtracting things in scientific notation. And remember, just like adding, subtracting like terms, you have to have like terms. So as an example, if you had 2x squared plus 3x squared, those are like terms because they have the same variable and the same exponent. Previously now, we kind of mostly said like terms are things that have the same variable, but kind of also implied in that was they also have the same exponent. So 2x squared and 3x squared are like terms, so you add them together and you get 5x squared. And remember, when you add and subtract, you do not touch the exponents. You only change the exponents when you multiply and divide. This is true of polynomials, monomials, and of scientific notation. So as a note, just kind of like fractions, you do not need common denominators to multiply and divide. Same thing goes here. You do not need common variables and exponents to multiply or divide. But with fractions, you do need a common denominator to add and subtract. Here the same thing goes. You do need like terms, meaning variable and exponent, in order to add and subtract. So I'm going to show you how, even if the question doesn't have it already, we can force it and make it work. Okay, so I may only do an example of adding, because subtracting is kind of the same thing, just subtract instead of adding. Alright, so let's say we had 6.89 times 10 to the 4th power plus 9.24 times 10 to the 6th power. So what we're going to do what we talked about before. We need like terms. But you'll notice, remember the like terms is kind of like this portion right here. Kind of like this could be thought of as x to the 4th power, but it's times 10 to the 4th power. This is times 10 to the 6th power. Well, those are not currently like terms. But the good news is we can kind of, because it's scientific notation, we can kind of fake it and make them look like they're like terms. So here's what we can do. We can kind of take them out of scientific notation, meaning we can move this decimal over a couple times. That way we had to move it back 2 times, so to where we could get to change this to a 6. Or we could move this decimal over 2 times, so that we would only have to move it 4 more times to get it to where it's supposed to be, and then they would have the same exponent. So you have your choice there. If I were to have my druthers, I would actually probably go with that one. That way we wouldn't, the second one I just showed you, that way we wouldn't have to deal with small decimals. So now we have like terms. They are like terms. So let me rewrite them the way we have them. We have 6.89 times 10 to the 4th power, and then what we're adding to that is 9.24, oh, not 9.24, it's 924 now, we moved it twice, 924 times 10 to the 4th power. So now, and if you're not sure if you're allowed to do this or not, feel free to experiment. 924 times 10 to the 4th power will equal the same thing as our original 9.24 times 10 to the 6th power. It'll equal the same thing. Alright, so just like with adding and subtracting, like we did up here, you do not change the exponent or the variable when you add and subtract, because you only affect the coefficients. So that means our answer when we add these is still going to be times 10 to the 4th power. We just need to figure out what is 6.89 plus 924. And that's going to give us 930.89. So 930.89. So we have our answer, but we want to express it in scientific notation. So here's what we got to do. We just have to imagine, okay, we see our starting point, the decimals between the 0 and the 8. We just need to move that decimal over so that it's between the 9 and the 3. So we need to move it over 2 times, which means in order to get back to, we have 9 point whatever, in order to get back to the 930, we need to make it bigger, which means we have to move the decimal bigger, so we need 2 spaces. So our 10 to the 4th power is going to become 10 to the 6th power. So what that means is we're going to have 9.3089 times 10 to the 6th power. That's going to be the scientific notation answer. It may not be a pretty answer because we got all those numbers, but that is the correct scientific notation answer to our original question. And not once did we have to worry about big giant digits that we may not have even been able to fit in our calculator, things like that. This was a much more attainable, easy to use question. It's especially useful for very large and very small numbers. Now I'm going to do what I said, where I'm going to give you an example of each, let you try them on your own. I may not explain them as fully, but I'll at least reveal the answers to you so you can check yourself. Alright, so give these 4 questions a shot. These are all the operations we've talked about. Press pause, give them a shot on your own, and then hit play and see how you did. Awkward silence. I hope you did that. Alright, so let's knock these out. So let's multiply those, I call them coefficients. Let's multiply those first. We get 8.97. 8.97 times 10, and now we add the exponents, so 2 plus 6 is 8, so times 10 to the 8th power, and that's going to be the complete correct answer to that first example. Now, if you haven't already tried the second one, press pause and try it now. Alright, just like before, if we have coefficients, go ahead and divide them as if this was from the dividing monomials video. 9.45 divided by 1.5 is 6.3 times 10. And now remember, when you divide, the quotient property of exponents told us to subtract those exponents for the common bases. So 10 to the 10th power, 10 to the 6th power, so you do 10 minus 6, and that's going to be 4. So 6.3 times 10 to the 4th power, that's going to be the answer to the second example. Make sure to hit pause if you haven't already tried the last two. Alright, we need quote-unquote like terms before we can add and subtract. So I'm going to go ahead and make this first one increase it by 2, so that I only have to increase it by 9 more instead of 11 more. That way they now have the same exponent. We're ready to go. So that means what we really have in that one is we have 950 times 10 to the 9th power plus 6.3 times 10 to the 9th power. So now we know our answer is going to have 10 to the 9th power in it. So 10 to the 9th power, we know our answer is going to have. So we just need to figure out what is 950 plus 6.3. And that's going to give us 956.3. So 956.3 times 10 to the 9th power. Well, that's not exactly scientific notation, so we need to put the answer in scientific notation. So as you can see, we have to move it twice. We have to move it twice, which means we now, to put it back, are going to have to make it even bigger by 2 more spaces. So this 10 to the 9th power has become 10 to the 11th power. So 9.56 times 10 to the 11th power. That's the answer to that one. Hit pause, try this last one if you haven't done so already. It occurs to me I totally left off of 3 on that last answer. It's 9.563. 3 doesn't disappear all of a sudden. Sorry about that. Let's try this last one. So we can avoid small decimals, just like I did the last one. I'm going to use this one. I'm going to make this one bigger by 2 spaces, so that now it's only 10 to the 7th power, because it's got to go up 9 spaces, but I just moved it 2, so I need to do a 7 more. So that means that's really 103 times 10 to the 7th. That's what I kind of turn into now. Then we're going to subtract out 4.7 times 10 to the 7th. And I did this because, like I said, I like to avoid those really small decimals. It seems to make things more complicated. So now add together these quote-unquote coefficients. I'm not sorry, not add. Subtract these quote-unquote coefficients, and then we'll see where we're at. They're going to give us 98.3. So we have 98.3. And remember, the exponent, or in this case, the variable, or excuse me, the times 10 to the 7th power stays the same. So that's still there. But we need it to be in official, unofficial scientific notation, so we need to move over one more time, which means our exponent needs to get bigger by 1 more so that it can still reach the same number, the same standard form. So that leaves us with 9.83 times 10 to the 8th power, and that's going to be the answer to that one. So at this point, you now had lots of examples of each of them, of doing computation with scientific notation. All the computation with scientific notation, they all related to the skills that we learn with our operations with exponents. Except for the adding and subtracting, we had to be a little creative to make sure they were quote-unquote like terms, so they had the same exponent on the tens. Good luck, guys, and let's move forward and take this to the next level.